What are the things I want you to think about here before we embark on data analysis proper, anomaly detection proper? There's some issues related to dimensionality. You might have heard that the more data you have, the better it is. And I mean, that's true, such as it is. You prefer to have more data than not enough data. But there's an issue related to the number of measurements you have for each observation. Unfortunately, if you have too many features, you are living in high-dimensional data sets, and because most of the methods that we use for anomaly detection rely on proximity of observations, high-dimensional spaces, nothing is close to anything else. Everything is far away from one another. A lot of the methods that we use are not applicable. So this has a name. It's called the curse of dimensionality. It's a real issue with data sets. You can overcome the curse of dimensionality by getting a lot of observations. The problem is that if you increase the number of variables you have in your data set by, say, 2, you need to have 4 times as many observations to be able to maintain your predictive power. And if you have 20 variables, well, you need 2 to the 20 times as many observations to maintain the predictive power. So I don't know how many variables your data sets actually have, how many features they have, but my suspicion is that if they have more than 5 or 6 or potentially 10 variables, you do not have nearly enough observations to really be able to work with the full complement of variables. And so you need to reduce the dimension of the data. Find the variables that matter the most for what you're trying to do if you want to be able to have somewhat powerful algorithms. So the solution to the curse of dimensionality is to either increase the size of your data set, but then that comes with other issues, big data issues, or reduce the dimensionality of the data set through feature selection or other dimension reduction methods. I'll talk about one method just briefly, just to say that it exists. Later on, we will look at data sets where we've assumed that the dimension has already been reduced so that we don't have to worry about dimensionality issues. When we speak of dimension, we are talking about the number of features, the number of variables, the number of things that are being measured for each observation. In a flat file setting, your observations are in rows, and the columns represent the things that you are measuring, the features, the attributes. If you're going to be talking about business intelligence, dimension means something else altogether. So just be aware that when I speak of dimensionality, I am speaking of the number of geometrical dimensions, physical dimensions, or mathematical dimensions, number of columns. Here's a nice little illustration of what I mean by the curse of dimensionality. And this is to sort of indicate or illustrate the fact that in high dimensional spaces, there aren't a lot of points that are close to one another. Everything is very far from. What you see on the left is a set of one-dimensional observations. So I've measured things between 0 and 1. Let's say there's 100 points in here, and they're uniformly distributed. Then there's about 42% of the observations that are captured by this little neighborhood. So roughly speaking, if I pick the midpoint, which is going to be at 1/4, and I allow myself to look at points which are within 1/4 to the right, within 1/4 to the left, I can find a neighborhood of the point 1/4. And all the points that are shaded here belong to that neighborhood. They're considered to be close to the point 1/4, point 25. It would make sense that you would get 42%, about 50% of the points, because these points are nicely distributed, uniformly distributed. And this interval here basically is half of the length of the full interval. So you would expect half of the points to be in that neighborhood. Now let's do the same thing with this two-dimensional data set. So this is the two-dimensional equivalent of what I've done here. I've generated 100 points with two variables, x and y. And the x's can go between 0 and 1, and the y's can go between 0 and 1. Now I'm going to pick a point which is the point 1/4, 1/4. And I'm again generating a neighborhood around that point where the width and the length will be 1/2. 1/2 being the same quantity as what I had here. So I'm going to say that anything which falls in the red box within 1/2 of the x length and 1/2 of the y length is going to be considered to be close or a neighbor of this point right here. I'm basically taking my original space and I'm chunking it down into 4 pieces, so each of the pieces should contain about 25% of the data. But here in this one specific example, it only contains 14% of the data, but that means that there's another quadrant that contains more than 25%, potentially 3 of them. But on average, about 25% of the data is captured by this neighborhood around the point. Now there's a bit of a change. It used to be that this neighborhood of length 1/2 captured 42% of the observations, but now this neighborhood of size 1/2 only captures 14% of the observations. So really this would be 50%, theoretically speaking, and this should be 25%. I mean, 42 and 50 are comparable, 14 and 25 are comparable, but here you can imagine moving up one extra dimension. We're going to have 3 variables instead, and we pick a point, and we're looking for a neighborhood of size 1/2 around it, so we go 1/2 in every direction, and this neighborhood here of that point is only 1/8 of the full space. So there's 8 other octets I can build here. And you can see by necessity that this same neighborhood of size 1/2, you would expect it to contain 12.5% of the data. In this specific example, only 7% of it is captured. What's happening is that as you increase the number of variables, the number of points that are captured on average reduces. And the reduction is, here you divide by 2, here you divide by 2, and so forth, but you only ever increase by 1 the number of variables. That's the curse of dimensionality. If you had 10 features, your neighborhood around this point here would be very, very small, and it would not contain any other points, or be very likely to contain any other points. That's the curse of dimensionality. You do not have neighbors anymore, or you have fewer and fewer neighbors. And if you don't have a lot of neighbors, you can't compare what is happening to you with what is happening to your neighbor. So if you have a missing value, for instance, you can say, let me just look at the observations that are close to me, what's happening for that value that's missing, and there isn't going to be people close to you. The nearest person to you will be very far away. Another way to look at this is that the size, the largest distances, keeps on increasing. This is size 1, this is size square root of 2, this is size square root of 3, and so the size, the diameter of your space gets bigger and bigger when you add more and more variables, even though everything is still bounded by 0, 1 here. Everything is in a box, and yet the diameter of the box keeps on getting larger and larger when you add more variables. That's a problem for analysis. I'm not going to say more about the curse of dimensionality. That's basically a known problem with data sets that are big, that have a lot of features. Do you need to use every single observation in your data set? You don't, depending on what you're trying to do. If you decide to pick rows randomly from your data set, you might have a representative sample, and that might be enough to train your anomaly detection models. But if there's not a lot of anomalies in your data set to start with, and you're not working with the full data set, you're working with the sample, it's conceivable that you will not have picked anomalous observations in your sample, and when you train your model, it will say, I can't find anomalous observations in here, there's no anomaly in this data set. And that's not really what you want. Your solution, in many instances, isn't to sample the observations, it is to sample the columns, to try to reduce your data set by only looking at a small number of features, trying to remove information or features that are irrelevant or redundant. Now, that requires you to do a little bit of analysis, rules-based analysis, to see whether something is useful or not. potentially having the number of the record might not actually provide you with more information down. Or it could be that one of them is the province's name and the other one is the province's code. Now, none of these values are the same. The provinces don't have the same name as their codes, but they carry exactly the same informational content. And you might be able to reduce the dataset dimensionality by removing these redundant variables. There's a number of approaches. We have filter approach versus wrapper approach. We also have unsupervised approaches versus supervised approaches. In supervised approaches, you are trying to train your model to make a specific prediction about the target of interest. And so when you do supervised feature selection, you're going to try to find the features that are more strongly linked with the thing you are trying to predict. So for instance, if you had a pre-built list of observations which were anomalous or fraudulent, then you could build a bunch of models with a variety of columns that are trying to predict whether something is fraudulent or not. And then you would usually find or pick the model that does a good job of making this prediction, but that has the fewest number of columns or predictors in it. That's a supervised feature selection approach. An unsupervised approach, removing information that doesn't give us more information, not necessarily about the thing we're trying to predict, just in general. Again, I will not be spending a fair amount of time here because I'm making the assumption that the data sets that we're working with have already been reduced, at least for this course. But if you're going to be doing this in the real world, you have to spend a fair amount of time reducing the dimension, removing features. One of the ways in which you can do this, and this is an unsupervised approach, it isn't based on what it is that I'm trying to do, is the principal component analysis approach. Roughly speaking, what you're trying to do with these data sets is to find the axes that would allow you to fit the best ellipsoid for the data. And if this axis here is substantially stronger or larger than the other axis, you might say, you know what? I'm not going to care about this axis. I'm just going to project all of my observations here on this axis. Instead of having a fully two-dimensional data set, I'm basically taking off my glasses, taking a few steps back and squinting and realizing that this is, roughly speaking, a line. Well, it isn't a great line here because the second principal component, the second direction, is actually fairly strong. The signal is strong. This would not be a good example of such a data set. But I can show you an example of something where this would work as well. So imagine you have the following points. These are all two-dimensional observations. There is a line of best fit here though, and you could decide to rotate your data set and basically view these as points on this axis. So even though this is a two-dimensional data set, you have an x and y coordinate, if you rotate your axes, you'll find that you wouldn't do that bad of a job by assuming this is in fact 5 points on the line. But that's the idea behind principal component analysis. You are not just sticking to 2 dimensions. In general, you might have 10 dimensions, and you might basically bring it down to 4 dimensions using projections. Again, I don't want to spend too much time talking about this, but the key takeaway is that you have to do something to try to reduce the dimension of your large dimensional data sets. There's other things you might need to do with your data before you can start analyzing it. Very often your models will require your data to meet certain assumptions. Like if you remember linear regression, when you first learned about it, you learned that you needed, for instance, the residuals to be normal. If you remember what the residuals are, let's say that these are my points from my line of best fit, and I compute these distances here. These are the residuals, the distances between the points in the line of best fit. These have to basically follow a normal distribution. So there's 5 assumptions in general that need to be met. And very often your data does not meet these assumptions. There's no reason why the data should meet these assumptions in general. So in order for you to be able to use the methods that you want to use, it's not going to be always as simple as linear regression, but it could be as simple as linear regression. You will need to transform the data to make sure that it meets the assumptions. That's one option. The other option is that you abandon the model. You can say, my assumptions are not met, I am not using this model. That's a bit of a scorched earth approach. I would consider trying to first see if you can transform the data into a format that your models can use. If you're going to be using the transformation approach, you need to be able to invert the transformation if you want to say something about the original data set. Very often you will say something about the transformed data, and that's useful, but that doesn't necessarily say something about the original data that you can take to a stakeholder. If we go back to the example of the PCA, this would be the real axes, the Cartesian axes, and you might find that the best axes would be these axes, something like this. So you've rotated the original set of axes by, say, 45 degrees. What this is saying is that now, every time you talk about your variables, you're not talking about x and y anymore. You might be talking about z and w instead. X and y might have made sense. X could have been the age, and y could have been the weight of a person, say. So if I tell you that x is equal to 13, that tells you that someone's age is 13. But if I talk to you about w and z, if I say that w takes on the value 12, well, this is going to be some combination of the x and the y. It could be like 25 minus 13. This would be the x value and the y value. It could be that w is meant to be x minus y, and 25 years minus 13 pounds. What does that mean? I mean, it is a number, it's 12, but it doesn't really mean something anymore. You can still analyze the numbers, come up with conclusions about things that make sense or don't make sense, but if you want to be able to answer the questions in the language that had been asked in, which is to say in the XY language and the age and weight language, you're sort of SOL without knowing what the inverse transformation is. Here's 3 very popular types of transformations for numerical values. If this was your original data set, you have an x and a y here. You're seeing that as you move over x, the variance in y increases, getting larger and larger. Well, that wouldn't be a good candidate for linear regression, because one of the things you're supposed to get in linear regression is that there shouldn't be an increase in variance or a decrease in variance when x changes. So you could consider some transformations that might help reduce this variance. The square, you can take the square of everything. Now the values are completely different, but there's still a fair amount of variance, and it still seems to be increasing. This would not be a good variance reducing transformation. The square root looks like it might be a better fit. And you're taking the square root of all of y values here, you're getting something where there doesn't seem to be nearly as, I mean, there's still a little bit more variance here and there, but not noticeably so. You might also take the reciprocal. So this would be y squared, square root of y, 1 over y. And that might be a good choice as well. And yeah, there's a few points where the residuals are pretty high, but if you take away these 2 points, this seems to be a pretty decent set of points. And these transformations might also help you identify potential outliers, things that at first glance you wouldn't have guessed that they were so different from the others, these 2 points right here. The reciprocal transformation gives you the suggestion that in fact there is something about them which is different. They don't really seem to follow the same pattern. Other things to think about, the idea of scaling. If you're going to be working with numerical variables, weights and heights for instance, they will have different scales. Being 6 feet tall sounds like I'm just like 1 unit taller than somebody who's 5 feet tall. And if I say I'm 220 pounds, I'm just 1 pound heavier than somebody who's 219 pounds. So the differences here look to only be 1, but the reality is that the difference between somebody who's 6 feet tall and 5 feet tall is much larger, much wider contextually than the difference between somebody who's 220 pounds and somebody who's 219 pounds. So putting everything on the same scales allows you to make more decent comparisons. So I am going to assume that the data has already been scaled. There's many ways to do these scalings. You could standardize them, which is to say you subtract the mean from every observation and you divide by the standard deviation. This is often something you need to do before you can apply other methods such as PCA. You could also decide to use a normalization. We're basically setting the range between 0 and 1. So before, if we had heights, presumably being 5 feet tall might be on the 0 end of the scale, and being 6.5 feet tall might be on the 1 end of the scale. And if I'm 6 feet tall, I'm right about here, 2/3 of the way, and somebody who's 5 feet tall is at the 0 end of the scale. Whereas for the weights, if you say that 100 pounds is at 0 and 250 pounds is at 1, then my 220 pounds would be here, and the 219 would basically be the same point. So this approach is actually a pretty good approach in general. It's something you should consider doing if you have numerical variables. If you're working with text variables, you can't do that. You can't scale your variables anymore. Doesn't make sense. But for numerical variables, this is something you want to do. Another thing you might want to do with your data to make it fit for consumption is you want to discretize it. If you have numerical variables, you might want to replace them by ordinal variables. Just to say, if you had a height, instead of having all the height values, you might end up wanting to use short, average, and tall. So that's fairly easy to do. You just write a bit of code that says, if it's above some value, you're tall. If it's below some value, you're short. If it's any other value, you're average. So that part is easy. The difficult part is to come up with good limits, good thresholds for these things. What is tall? What is short? Like, I'm 6'1", so for me, 6'1" isn't really considered tall. It's my everyday average. But at 6'1", I'm basically 87th percentile of heights for males in this country. So I should definitely be considered tall. And, if you're 5 feet tall, presumably you're short. But what about 5'6"? Well, 5'6" depends. Are you a man or a woman? And if you're using bins for your heights, and you also have gender as a variable, then do you have a specific discretization for females and a specific one for males, or it's meant to be the same one? Because if it's meant to be the same one for both, you're going to get a lot of men in the tall category and a lot of women in the short category. And there's also a question of context. 6 feet tall, or 6'1", is tall in Canada, but it's not anomalously tall. It's just tall. But 6'1" in Bolivia, you're a giant. Short, average, tall, what is the methodology that we use to separate those? And we sort of understand that short and average and tall, there's an order to them. But if you decide, for instance, to say, I'm going to pick 33% of my observations and put them in the short bin, and 33% of my observations and put them in the average bin, and 33% of the observations and put them in the tall bin, then you might end up with bins that look like this in terms of the possible heights. So perhaps short will be between 5 and 5'4", then average could be between 5'4" and 5'10", and then the rest would be between 5'10" and 6'8". And the length here isn't the same for each of the bins. Is this a problem? It might be, it might not be, it depends on your situation. You can decide instead to have all of the bins having the same width, from 5 to 6'8", but if you do that, then you might get some weird numbers in between here. Numbers that you would not necessarily associate with being short. Let's say 5'8" here. And then this would be about 6'1". Yeah, some of those would be short for sure, and some of those would be tall for sure, but you would sort of assume that some of those should also be tall, and some of those should also be tall, not average. I would find myself in the average category then if you use the same width. So it sounds ridiculous to even spend too much time thinking about this, but that could definitely affect how you end up analyzing your data at the end of the day. You might also think about creating variables. Like when you discretize a variable, you also created a variable. Then if you're going to do this, you need to have some idea as to the functional relationships at play. And that requires you to have system understanding. You can easily create a variable from a numerical perspective or from a categorical perspective. It's easy to create one. But if you want this variable to be useful, you need to have an idea as to where it fits in the overall scheme of things. I'll end by talking about data quality and data validation. What is it that you need to be on the lookout for? Ideally, your data sets will be sound. You want data sets that you can trust, that you can rely on. And they should have as few issues as possible with validity. The data that you have is of the right type. It's in the right range. If you had responses that were mandatory, you do not have missing values. If you have responses that had to be unique, you do have uniqueness. So for instance, if we're measuring number of kids, you would expect that number to be non-negative. And you'd probably expect that number to be smaller than what? 5, 6? I mean, it's possible to have more than 6 kids. That shouldn't happen too often. There's a range of potential values that you'll be interested in. In terms of completeness, as few missing observations as possible is what you want. You want the things that are being recorded, measured, to be accurate and to be precise. There should be as little measurement error or data entry errors as possible. There should be consistency. If you say that you have no kids, but then you tell me the age of your oldest kid is 13, something here is not consistent. I don't know which one of these two is not the right answer, the right measurement, but I know they can't both be right simultaneously. And finally, there's got to be questions of uniformity. Are you using units uniformly throughout? If I'm asking you what your height is, how many of you would respond using the metric system, and how many of you would respond using the imperial system? Even though I'm French-Canadian, like, the metric system isn't used to talk about heights in Canada, at least not for people who grew up in it. But a lot of my students come from Romania or China or other countries, and there the metric system is used. Like, I have no clue what my height is in centimeters. I know I'm 6 feet tall and there's about 30 centimeters to each foot, so I'm about a tad over 180 centimeters. But I have to think about it. And if you tell me how tall you are in centimeters, it means nothing to me. Same thing with my weight. I have no idea what my weight is in your metric system. So if you go online and you fill in information and you have these free fields to enter, and you ask me what my height is, I'm going to write 6'1". Obviously, I'm not talking about centimeters. But if somebody else that comes from Romania, say, sees this question, they might say, I'm 172. Obviously, these cannot be inches. If you have a data set with 1,500 observations, and only 3 of them are answered using the imperial system, you might not spot them right away. So you need to set up your data collection procedures and your data cleaning procedures so that they can capture these things. And if you look for the data quality issues early on, you will save yourself a lot of headache. In terms of the measurements, in terms of making sure that what you're measuring actually measures what it's supposed to measure, you need to have some audit system. Ideally, your measurements should be accurate and precise. If you're trying to measure the bullseye here, that's meant to be your quantity of interest, well, there'll be a bit of noise. No instrument is perfect 100% of the time. There'll be some measurement error. You want it to be not very widespread, and you want it to be focused on the right quantity or centered on the right quantity. You have instances where the measurements are precise but perhaps not very accurate. Think of having a scale which for some reason has been misaligned. So when you're not stepping on the scale, it already says 2 pounds. It could very well be that it's quite precise other than that, just that you'll never get your real weight. You'll always be about 2 pounds away from your real weight. You might also have measurements that are accurate in the sense that their average is close to the real thing. Like, it makes errors in every direction, but centered on the real value, except it's not very precise because the errors are quite large. And finally, you might have measurements that are neither accurate nor very precise. You try to avoid these situations. You need to have some way to audit your data. Do you know in which of these cases you find yourself? What are the sources of errors you might deal with? This is especially the case if you're dealing with data sets that are legacy data sets that you cannot control. You've inherited them, or they've been combined or merged with other data sets that have different standards than the ones you have in your data set. It could be that a missing data point has been given a code. Whenever you see a 99, it's meant to be, oh, we didn't have data for that, so this is a missing data. We're writing it down as 99. The problem with that is 99 is 99. And if, say, it's the number of kids that you have, and you didn't answer, and they put a 99, and you compute the mean, well, that's going to drive the true value away from the estimate that you'll provide. Now you might say, well, I'd noticed that there was a 99 in my data set. Yeah, if you have 12 observations, you would notice that one of them is 99. But if you have 20,000 observations and 12 of them are 99s, well, you will be changing the true mean in real ways, but you will not be able to spot it just by looking at the mean value. Your NAs might have been given a code. There might have been data entry errors, coding errors, measurement errors, a lot of duplicate entries that don't look like they're duplicate entries because they're not next to one another in the data set, or they've been given a different row number or different item entry number. There's also issues related to heaping. I don't know if you're familiar with heaping. If I ask you what time it is right now, well, most of you will say it's 2:45. You're not going to say it's 2:43. You might even say it's about 3. 2:43 is, well, it takes a special kind of mind to answer 2:43 to a question of what time it is. How many hours did you work yesterday? 10 hours? It looks like you worked 10 hours. You didn't work 10 hours. You might have worked 10 hours and 17 minutes or, some other number. You'll say 10 hours because it's simple. Is the data subject to this type of subjective reporting? Or is it being measured by a sensor? I worked with a firefighter's data set once, and we were looking at when emergencies occurred. And would you believe that they tend to occur on the hour? 1 o'clock has like a substantial larger number of emergencies than 1:17. Why? Why should that be the case? It's because when they do the recording of these emergencies, they'll just give you a rough estimate of the time. Can you recognize that in your data set? Is this something that you're going to be working with? How do you detect entries that are invalid? Like this 99 for the number of children you have, how would you find that? Well, you have to look at your statistics. You need to know how to summarize data, both on the univariate front. Can you come up with the range, the z-scores, the means, the quartiles, the standard deviations, the kind of stuff you would have learned about in a first or second year statistics class. There's also multivariate descriptive statistics where you look at combinations of things. If one of your questions is how many pregnancies did you have, and the other question is how old are you, well, you should be able to see on its own the number of pregnancies for each individual in the data set, and you can look at the age distribution and you might see things that make sense. But when you combine the two of them together, if you see somebody who's 5 years old who's had a pregnancy, there's a problem there. Now, you would never look at somebody being 5 years old as being problematic. It's an acceptable age. And you would never look at somebody having had a pregnancy as being problematic, but if the pregnancy is for a 5-year-old, there's a problem. Adding dimensions to your descriptions might actually help you find things that are invalid, that are illogical. Data visualization might also help. It helps because it helps you find outliers, things that don't look like they should belong where they currently are. Very important lesson for you is that if you fail to detect an invalid entry, it doesn't mean that your entries are all valid. All it means is that you weren't able to detect an invalid entry. And that lesson also works for anomalous observations and outliers. Failure to detect anomalies doesn't mean that there are no anomalies. It just means that your algorithm didn't catch an anomaly. What do you do with invalid entries when you catch them? Sometimes you're able to fix them. You see, oh, this is exactly what happened. Let me fix that. If you only have a small number of invalid entries in your data set as a whole, you might as well record them as missing and then treat them as regular missing values that you will impute or find a replacement value for. If you have too many invalid entries, that's probably a sign that something is not going well. I gave you this example when we talked about anomalies in general, but here you have a clear-cut proof that one of these observations is not like the other. Something about it is invalid. Anomalies aren't always going to be invalid entry. It could be the true entry is actually something different. That's a possibility. Either it's your understanding that's off, or the entry that was entered is off. Who knows? There's no guarantee that this is a wrong value. I'll give you another example. This is a histogram of the time of arrivals at a screening station at the airport prior to the time of departure, in minutes. Now, typically, when you travel, how early do you show up at the airport to be processed and scanned? For myself, if it's a local flight, an hour before the flight. International flight, especially if I'm traveling through the States and you have to go through customs first, perhaps, a few hours before, 3 hours before. But if I'm traveling to Europe, I might just show up 2 hours, an hour and a half before. Look at this data set here. So this is a time of arrivals at screening station prior to departure. Not a single person has arrived later than 2 hours and a half before their flight was scheduled to depart. As a whole, this distribution makes sense. Most people showed up, here. It's a fair number of people, 140,000. And I get a few people who are, show up way earlier and a few people who show up a bit later. So that shape makes sense. But the fact that there isn't a single person who showed up later than 2.5 hours before the flight was scheduled to depart is problematic. So none of the observations here are at fault, or rather, they are all at fault. Something is wrong with this scale. This doesn't make any sense. Unless you're sending people to the moon. Is this a rocket ship? Yeah, for a rocket ship, that would make sense. You're going to outer space. You'd want to be there plenty of time before it's supposed to start. But this is an airport. What's actually happened here is that the scale was actually wrong. We were reporting according to Eastern Standard Time for one of these, the arrivals, and the other, the departure, was actually being reported using the local time. And so in reality, what you were seeing is that there was going to be a number of people here who missed their flights. This difference here is not due to people showing up 2.5 hours before they were supposed to leave. And the data said when you were reporting it, something was wrong. So sometimes the invalid concepts or context applies to the entire data set as a whole, not just to a specific observation. It's something you have to develop an intuition. Main takeaways here: don't wait until after the analysis is done to find out there was a problem with data quality, because you have to fix the problems and rerun the analysis and re-release the results, and that's not good optics. If you just do univariate tests, you might not be able to tell the whole story. So take the time to combine more than one variable together. This is something we'll talk about when we talk about anomaly detection. Visualizations would help you spot things, assuming that you're not working with too many dimensions to start. If you have a 10-dimensional data set, it's a bit hard to visualize it in a consistently useful map. And we've said this before, but I need to reiterate it. Context is super important. It always depends on the context. You need to understand your data set, what it means, before you can move on to do the analysis. You need to understand the data set quality as